There is a specific category of classic car part that mechanics from the golden era quietly understood. These parts did not wear out. They did not crack under pressure or fail over decades of steady use. But because regulators decided they had to go, some were pulled from the market by the EPA. Some were banned under international treaty. Some are illegal to install on a road car today, even though the parts themselves are still mechanically sound. If you are restoring or buying a classic right now, and you do not know which parts these are and what they mean for your build, you are working without the full picture. And I've put together this list for the people who want to understand the machine, not just look at it. Asbestos brake linings. The first part on this list is one that completely rewrote the industry standard for friction materials, and the replacement product still has not fully caught up. Asbestos brake linings were standard equipment on virtually every passenger vehicle built in the United States and Europe from the 1920s through the mid-1980s. The material was woven or compressed into brake shoes and pads, and it performed in a way that modern friction compounds have spent 50 years trying to replicate. What made asbestos so effective as a brake lining came down to three properties working together. The first was its heat resistance. Asbestos fibers begin to degrade at temperatures approaching 1,000 degrees Fahrenheit, far beyond the thermal threshold of a normal street car's braking system under any realistic driving condition. Standard disc brake rotors on a street-driven vehicle rarely exceed 400 degrees Fahrenheit even during hard stops. That gap meant asbestos linings were operating at a fraction of their thermal limit every single time you press the brake pedal. The second property was dimensional stability. Asbestos did not expand significantly under heat, which meant the coefficient of friction stayed consistent from the first stop of the morning to the last one of the day. You got the same bite whether the brakes were cold or hot after a long mountain descent. Third was mechanical durability. The fibers had tensile strength sufficient to resist the constant shearing and grinding forces of metal-on-metal contact without breaking down rapidly. The practical result of these three properties combined was longevity that modern brake pads simply do not reach. Mechanics who worked on American cars from the 1950s and 1960s routinely report that original brake shoes were still serviceable after 80,000 to 100,000 miles of driving. In some documented fleet vehicle histories, taxi companies, government fleets, utility vehicles, original asbestos lining sets were logged past 120,000 miles without replacement. This was not exceptional performance. This was routine. The brake lining was not a consumable the way a modern pad is. It was a component that lasted the life of the application. The reason these parts are gone is well documented. Asbestos fibers, when disturbed during installation, removal, or brake dust exposure in service, become airborne in a respirable form. That causes mesothelioma and asbestosis with sustained exposure. The EPA began addressing asbestos-containing automotive friction materials in the 1970s. By the late 1980s, major manufacturers had voluntarily stopped production. The United Kingdom formally banned asbestos in vehicle friction materials. In 1999, the European Union followed with comprehensive coverage across the whole continent. In the United States, the regulatory situation is more complex. The EPA's 1989 attempt at a complete asbestos ban was partially overturned in federal court in 1991. But market forces and liability exposure effectively ended domestic production regardless. Here is what this means for the classic car buyer or restorer. Any Preminus 1980 vehicle you purchase that still has its original brake assembly may have asbestos-bonded shoes or pads installed. This is not a selling point. It is a safety and handling concern, not because the friction material has structurally failed, but because original linings of that age have hardened and glazed. With time and heat cycling, they need replacement before the vehicle is driven, but the reason they have not crumbled or disintegrated is because the material was genuinely that durable. When a seller tells you a car still has its original brakes, that is not reassurance. That is a clue about what you are dealing with. Handle the components accordingly. Replace them with modern approved compounds, but understand clearly that you are replacing something that mechanically never quit. Asbestos clutch facings, the second part, follows the same chemistry, the same regulatory outcome, and the same story, but it played out inside the drivetrain rather than the braking system. Asbestos clutch facings were the standard friction interface between the flywheel and the pressure plate on virtually every manual transmission vehicle built through the mid-1970s. And in terms of raw longevity under repeated thermal and mechanical abuse, they were in a category of their own. Clutch operation is mechanically brutal in a way that is easy to underestimate. Every time you release the pedal from a stop, the facing is slipping, generating heat, absorbing shock, transmitting torque through a disc that has to survive that process tens of thousands of times over the service life of the vehicle. The energy involved in a single clutch engagement from rest is significant. Multiply that across 15 or 20 years of regular use, and you understand why clutch replacement was considered a routine maintenance event for most of automotive history. It was expected to happen at least once in the car's life, often twice on hard-driven vehicles, with asbestos facings for a great many drivers in the classic era. It happened once, or never. The asbestos fiber used in clutch disc facings was typically woven into a composite matrix, reinforced with brass or bronze wire for additional structural integrity, then impregnated with a binding resin under compression. This produced a facing that resisted heat fade under sustained engagement loads, which is critical because the alternative is a clutch disc that glazes and loses bite progressively as it approaches its thermal limit. Once a friction disc glazes, engagement becomes either too abrupt or too soft depending on temperature, and the problem compounds with each use cycle. Asbestos facings retained their friction coefficient through heat cycles that would compromise later organic compounds, and they did so without the harshness of ceramic facings that were developed later for performance applications. Fleet operators running delivery vehicles and commercial trucks on asbestos-lined clutches documented service lives that looked implausible on paper until you understood what the material was capable of. There are documented commercial vehicle records showing original clutch facings still in service with functional friction surfaces at 150,000 miles and beyond, in vehicles that made multiple stop-and-go deliveries every working day. That is not luck. That is material science working correctly. For the classic car market, this carries a direct implication for how you read a vehicle's history. If you acquire a vehicle built before 1975 that is documented as never having had its clutch replaced and has verifiable low mileage, the facing inside is likely an asbestos composite. Whether it is still serviceable depends on mileage, storage conditions, and whether any oil contamination has reached the clutch. But it did not survive in one piece because it was cheap or brittle. When you replace it, you are not correcting a failure. You are performing a mandatory materials change for safety and regulatory compliance. That distinction matters when you are reading what a car's maintenance record actually tells you about how it was kept. The ban on asbestos clutch facings followed the same regulatory path as brake linings. EU Directive 1999/77/EC effectively ended asbestos use in all automotive friction components across Europe. U.S. production wound down through a combination of EPA regulatory pressure and legal liability exposure. The replacement materials available today, organic composites, Kevlar fiber compounds, ceramic friction materials, are competitive and in some applications superior, but they required years of development to approach what asbestos delivered from the beginning of its production history. Our -12 refrigerant systems, the third part, does not involve friction material or heat-resistant fiber at all. It involves a refrigerant that was so chemically stable and so precisely matched to the automotive AC systems built around it that the original compressors running what they were designed to run simply did not fail. R-12, sold commercially as Freon, manufactured by DuPont, was the standard refrigerant for automotive air conditioning systems from the early 1950s through the early 1990s. The compressors built to operate on R-12 pressure curves and lubrication characteristics have a service record that is difficult to argue with. The AC compressors installed in American cars during the 1960s and 1970s, manufactured by York, Frigidaire, and Sandon, among others, were engineered to operate within a specific pressure window. R-12 has relatively low operating pressures on both the high and low sides of the system, compared to its replacement refrigerant. It also carries the compressor lubricating oil very efficiently through the system, meaning internal compressor components, pistons, reed valves, bearings, receive consistent lubrication throughout every operating cycle. The oil does not pool, does not separate, and does not leave dry spots inside the machine during startup. Original AC compressors from full-size American cars of this era, when maintained in sealed systems with no moisture intrusion and no refrigerant contamination, routinely ran for 30 and 40 years without requiring any internal service. Many are still operational today, not rebuilt, original. Then R-12 was banned. The Montreal Protocol, signed in 1987 and ratified internationally through the early 1990s, identified chlorofluorocarbons as primary contributors to stratospheric ozone depletion. R-12 is a chlorofluorocarbon. The protocol mandated that production and import of R-12 be phased out in developed nations. In the United States, new production was phased out by 1994. The EPA regulated the sale and recovery of remaining stockpiles. What had cost a few dollars per pound became a premium commodity on the secondary market, still traded legally in certified quantities to this day. Replacement refrigerant, R-134a, operates at higher system pressures. Those higher pressures are harder on the shaft seals in original R-12 compressors, components that were designed for the lower pressure environment they were built around. Converted R-12 systems running R-134a tend to develop shaft seal leaks, more commonly than original R-12 systems that were left intact. Additionally, R-134a is measurably less efficient at heat transfer than R-12, meaning converted systems frequently deliver less cooling capacity than the original system was rated for, which becomes obvious during a hot summer afternoon. In a converted 1968 Cadillac or a big block Chevelle with a factory AC option. What this means practically is that an original, unmodified R-12 AC system in a classic car that has been properly stored and maintained with a sealed charge is a mechanical asset, not a liability. Restorers who understand this do not immediately convert these systems. They source legally available, certified R-12 from licensed refrigerant recovery inventories, verify system integrity with a leak test, and preserve what they have. Converting a functional R-12 system to R-134a requires a full seal replacement, an oil flush, and often condenser upgrades to compensate for efficiency loss. It is not a trivial job, and if the compressor was working perfectly on its original refrigerant, the conversion introduces new failure points that were not there before. The lesson from R-12 is not that you should work around refrigerant regulations. It is that the original engineering was so well matched to its operating environment that the system ran without failure for decades, and it was a regulatory change, not mechanical inadequacy, that ended its production life. Lead tin body solder. The fourth part is one that separates genuine coachwork from everything that came after it. Lead tin body solder, applied with a torch and a wooden paddle to fill seams, smooth transitions, and restore contours on automobiles since the 1930s, creates a bond with sheet metal that no subsequent body filler technology has replicated in the same way. It does not adhere to the surface, it alloys with it. That distinction is fundamental to understanding why original lead work is still intact on 60-year-old bodywork, while polyester filler repairs from 20 years ago are already showing bubbles. Standard polyester body filler, the product most people associate with collision repair since the 1960s, bonds to the outer surface of the steel through mechanical adhesion. It cures to a rigid mass that expands and contracts at a different rate than the underlying metal as temperatures change through the seasons and through daily heat cycles. This differential movement eventually opens microscopic gaps at the bond line. Moisture finds those gaps. Rust begins beneath the filler layer. A blister appears years later, sometimes a decade later, sometimes two, and by the time it is visible from outside, the damage underneath is already extensive, and the repair footprint is larger than what you started with. Lead tin solder, typically in a 30-70 or 40-60 ratio of tin to lead by weight, behaves differently because of how it is applied. The steel is tinned first. A thin coating of flux and metallic tin is worked into the prepared surface with heat and a brush, creating a chemically receptive layer bonded to the steel. The lead tin rod is then applied to the heated panel, flowing into the tinned area and shaped smooth with a forming paddle while still soft. At application temperature, the solder fuses with the tin layer and through it into the steel itself. The bond is not adhesive, it is metallurgical. There is no distinct interface between the filler and the metal because there is no interface. They become continuous. The result is a repair or finished surface that expands and contracts with the steel because it is, in the most practical sense, part of the steel. Moisture cannot penetrate a correctly applied lead seam because there is no seam. There is only metal. Original lathe-worked coachwork on American luxury vehicles from the 1940s, 1950s, and 1960s. Lincoln Continental convertibles, coach-built Cadillac bodies, high-spec factory restorations, is intact today with no evidence of lifting, cracking, or corrosion beneath the worked areas. 60 years on, in some cases more, the lead is performing exactly as applied. Lead tin body solder is now effectively prohibited for general automotive bodywork under EPA lead hazard regulations and OSHA workplace exposure standards. California's industrial hygiene regulations made lead-based body solder application in commercial body shops essentially non-compliant by the early 2000s. The EU's End-of-Life Vehicle Directive restricted lead use in automotive manufacturing. The material is not entirely illegal to handle in every jurisdiction, but the regulatory burden on commercial shops and the liability exposure from lead dust management has made it functionally unavailable in mainstream restoration practice. For the serious restorer evaluating a classic, original lead work is a feature to be identified and preserved. When you find a panel that has been lead worked correctly and is still intact, you protect it and refinish over it. The alternative, grinding it out and replacing with modern polyester filler, is technically inferior in every measurable way except cost and regulatory simplicity. When a car comes to you with original lead seams that are still clean and tight, the previous coach builder gave you a gift. Respect it. If you are finding this useful, drop a comment below and tell me which of these you have run into in your own restorations. This channel is built for people who actually get under the cars. Your experience adds to this conversation in ways that I cannot cover alone. Hexavalent chromium plating, the fifth part, is visible on virtually every show-quality American car from the 1950s, and nearly every restorer working today either cannot reproduce it correctly or is paying a significant premium to one of the few remaining certified shops that can. Hexavalent chromium plating, the original automotive chrome process, produced a surface finish so corrosion-resistant, so hard, and so dimensionally consistent that original chrome components from 60 and 70 years ago regularly come in for restoration in better condition than modern trivalent chrome parts do after 10 years of outdoor exposure. The traditional automotive chrome plating process involved three stages built on top of one another. First, a copper undercoat was applied to create a fully conductive, pore-free base layer that covered any microscopic surface irregularities in the base metal. Second, a nickel layer, typically a dual-layer system with semi-bright nickel followed by bright nickel, was deposited over the copper. This nickel layer is where most of the actual corrosion resistance of a chrome finish resides, and the quality of the nickel work determines how long the finish lasts in the real world. Third, the chrome layer was applied from a bath of chromic acid, hexavalent chromium, CrVi. This top coat provided extreme surface hardness, a characteristic blue-white color, and a surface so dense that atmospheric moisture, road chemicals, and UV radiation had limited ability to penetrate it or initiate corrosion. Original American cars from the 1950s and early 1960s, chromed correctly using this process, had bumpers and exterior trim that remained visually correct for 20 to 30 years of regular outdoor exposure without replating. This was not just an aesthetic quality. In industrial and aerospace applications, hard chromium coatings deposited using hexavalent chromium were applied to hydraulic cylinder rods, aircraft landing gear, and bearing journals because the coating extended the working life of metal components beyond their original specification. The chemistry was that effective. Hexavalent chromium is a human carcinogen. The occupational health evidence is not ambiguous. Sustained exposure to CrVi in plating shop environments causes lung cancer in workers. OSHA issued its hexavalent chromium standard in 2006, imposing a permissible exposure limit that required significant capital investment in ventilation, air monitoring, protective equipment, and medical surveillance. Many plating shops, particularly smaller operations, closed rather than comply with those costs. The EU restricted CrVi use under the REACH regulation, requiring special authorization that is time-limited, expensive, and increasingly difficult to obtain. In the United States, shops still legally operating CrVi plating are doing so under some of the tightest environmental and safety requirements in any industrial category. The replacement process, trivalent chromium plating using Roman III, is less carcinogenic and significantly easier to manage from a regulatory standpoint. It is also measurably less durable. Trivalent chrome does not produce the same hard, tightly deposited surface layer. Its corrosion resistance in long-term salt spray testing is lower. Color matching original hex chrome with trivalent chrome is a recognized technical challenge in restoration work. The color tone sits slightly differently under light, and it shows on highly visible trim pieces when only part of a component has been replated. For the buyer of a show-quality classic, understanding this distinction directly affects how you read a car's presentation and what restoration work means to its value. Original unrestored chrome that is still in serviceable condition is worth preserving exactly as it sits. Replated trim, unless it was done by one of the remaining certified hex chrome operations, is a step down from what was there originally, even if it looks correct from 10 feet away. Crankcase road draft tubes. The sixth part is one that most people working on Preminus 1,963 American cars have seen and replaced without fully understanding what they were replacing or why. The crankcase road draft tube was the original crankcase ventilation system on virtually every internal combustion engine built before emissions regulations mandated the positive crankcase ventilation valve. It was passive, it was simple, it had no moving parts whatsoever, and in over 60 years of standard production use, it almost never failed. Understanding what it did requires a quick look at the crankcase environment. The lower section of any reciprocating engine, The area enclosing the crankshaft and the bottoms of the connecting rods accumulates blow-by gases during normal engine operation. These are combustion gases that slip past the piston rings on the power stroke and collect below, mixing with oil vapors in the crankcase atmosphere. If those gases are not removed continuously, they pressurize the crankcase, attack the integrity of oil seals throughout the engine, contaminate the oil with combustion byproducts, and accelerate internal wear across every lubricated surface. Managing crankcase pressure is not optional. It is fundamental to how long an engine survives. The road draft tube solved this problem with pure physics and no moving parts at all. A tube ran from a port in the crankcase, often the oil filler tube or a dedicated breather port, down to an exit point below the chassis, facing rearward or downward. The aerodynamic effect of airflow under a moving vehicle created a mild but consistent negative pressure at the open tube exit. That low-pressure zone drew crankcase gases out of the engine and dispersed them under and behind the vehicle. No valve, no orifice, no spring, no diaphragm. Just a tube, open at both ends, using vehicle speed to breathe the engine. The positive crankcase ventilation valve, what every modern technician calls the PCV valve, replaced the road draft tube starting in 1961, when California first mandated it on new vehicles sold in that state. The federal government required PCV valves on all new passenger cars, beginning with the 1963 model year. The road draft tube was not outlawed because it failed to ventilate the crankcase. It was banned because it vented hydrocarbons directly into the atmosphere below the vehicle, contributing to the photochemical smog that was already choking major cities by the late 1950s. The regulation was an emissions decision, not an engineering one. Here is what the switch actually cost in mechanical terms. PCV valve is a maintenance item. It contains a spring-loaded plunger that meters crankcase gas flow into the intake manifold, where those gases are reburned in the combustion process. When a PCV valve sticks open, it creates an unmetered vacuum leak, and the engine runs lean. When it sticks closed, crankcase pressure builds and oil seals begin to fail, often the rear main seal first, then the valve cover gaskets. The valve requires periodic inspection and replacement, generally every 30,000 to 50,000 miles. And on engines with significant blow-by, it can require replacement more often. The road draft tube required no periodic maintenance at all. It was a piece of formed tubing with no restriction and no moving components. Under normal operating conditions, it could not clog because there was nothing to clog. The gases moved freely through an open passage. It could not fail mechanically because there was no mechanism. The only failure modes were physical damage to the tube itself or severe corrosion breach, both of which were immediately visible and repairable with basic equipment. On well-maintained pre-war and early post-war engines, the road draft tube was still functioning exactly as designed decades after the car left the factory floor. For the restorer working on any vehicle built before 1963 that is going back to original specification, the road draft tube is the correct component. Installing a retrofit PCV system because it looks more modern is a modification, not a restoration. Whether it is appropriate depends entirely on what you are building the car for and where you intend to drive it. But understanding what the original system was, how it functioned, and why the regulation replaced it gives you an honest picture of the engineering that was there and what was added to it in the name of emissions compliance. Soft cast iron valve seats, the seventh part, requires understanding one of the most significant mechanical relationships in the classic engine: the connection between the fuel that went into the tank and the condition of the valvetrain inside the head. Soft cast iron valve seats were standard in virtually every production gasoline engine built before the early 1970s. They were effective, durable, and self-maintaining. As long as they had access to one specific compound in the fuel supply, that was eventually removed entirely from road-use gasoline. Valve seats are the hardened contact rings in the cylinder head, against which the intake and exhaust valves close to seal the combustion chamber on every cycle. Every valve closure is an impact event. The exhaust valve is doing this under conditions of extreme heat. Exhaust gases exit at temperatures that can exceed 1,200 degrees Fahrenheit under load, and the exhaust valve face and seat are exposed to that heat continuously. For the valve seat to survive hundreds of thousands of opening and closing cycles under those conditions, it either needs to be very hard, as modern hardened steel insert seats are, or it needs a continuously renewed sacrificial lubricating layer between the valve face and the seat surface on every cycle. Soft cast iron seats in pre-1970s engines relied on the second approach. Tetraethyl lead, the octane-boosting additive blended into gasoline since the early 1920s, deposited a thin, soft layer of lead compounds on the valve seat surface during every combustion cycle. This lead film acted as both a lubricant and a cushion. The exhaust valve was not striking bare iron with each closure. It was striking a surface that was continuously renewed with a microscopic layer of soft lead deposit. The result was a valve seat that, under normal operating conditions with leaded fuel, essentially never receded, never eroded, and never required service for the life of the engine. The EPA mandated the progressive removal of tetraethyl lead from the U.S. fuel supply in stages. Leaded fuel was required to be phased out beginning with 1975 model year vehicles equipped with catalytic converters, which the lead additive poisoned irreversibly. By 1996, leaded gasoline for on-road use was completely banned in the United States. Europe and most other developed markets followed through the late 1990s and early 2000s. Without lead in the fuel, soft cast iron seats lose their protective deposit film on every combustion cycle. The exhaust valve strikes bare iron repeatedly under extreme heat. The seat surface begins to erode, a condition known in the industry as valve seat recession. On a highway-driven vehicle, with a pre-emissions engine still running its original soft iron seats on modern pump gasoline, measurable recession and compression loss can develop within 20,000 to 30,000 miles. In more severe cases, the valve sinks into the head far enough to lose effective sealing on that cylinder. It presents as a compression loss that gets worse under sustained highway speed, exactly the type of symptom that gets misdiagnosed as a head gasket issue when the real problem is in the seat interface. The modification is well understood and not complicated for a competent machine shop. The original seat material is cut out on a bore mill, and hardened steel insert seats are pressed in under interference fit. The inserts are made from tool steel alloys that do not rely on lead lubrication, because the material itself is hard enough to resist the contact wear. It is a one-time fix. It is a direct consequence of a regulatory decision, removing something from the fuel supply that was never a mechanical problem as long as it was there. When you evaluate a Preminis 1971 engine for purchase or restoration, this is one of the first questions you ask. Has it been converted for unleaded fuel use? If the answer is no, and the engine has regular highway driving logged since the mid-1970s, you need a valve inspection and likely a valve job before you can make any accurate assessment of overall engine health. Not because the engine was poorly built, because the fuel it was built around no longer exists. Asbestos head gaskets. The eighth and final part sits at the most critical sealing point in the engine, a component that, in its original asbestos composite form, had a failure rate on well-maintained engines that mechanics from the era consistently describe as very low. Asbestos head gaskets were the standard combustion seal on gasoline and diesel engines from the earliest years of the automobile through the late 1970s and into the early 1980s. They were conformable, chemically resistant to oil, coolant, and combustion byproducts, and remarkably forgiving of the imperfect surface conditions that characterized production engine machining tolerances of the era. Consider what a head gasket is being asked to do. It must simultaneously seal combustion pressures exceeding 1,000 psi on the power stroke, seal coolant passages carrying pressurized water at temperatures approaching 200 degrees Fahrenheit, seal oil galleries from contamination in both directions, and do all of this while compressed between two dissimilar metal surfaces, typically an iron block against an iron or aluminum head, that expand at different rates as the engine cycles through heat. It must flex without cracking, seal without extruding under pressure, and remain intact through tens of thousands of thermal expansion and contraction cycles over the operating life of the engine. Stop scrolling through listings based on paint color and year. Start looking for these specific technical markers. Ask whether the head gasket has been replaced and when. Ask about the valve seat modification history on anything Preminus 1971. Look at original chrome quality and learn to tell the difference between correct plating and a cheap respray with chrome aerosol. Find the original AC compressor and determine whether it has been converted or left intact. These are the questions that separate informed buyers from expensive mistakes. One correct purchase, made with this kind of mechanical literacy, is worth more than a dozen transactions made on looks and instinct. That is what this channel is for. If you want to keep building this kind of knowledge, subscribe, stay with us, and bring your experience into the comments. The more you know going in, the better what comes out of your garage will be.